Hello and welcome to a brief demonstration on how to do trigonometric integrals. We open up with the most popular format, and that is the product of powers of sines and cosines. So here we're going to practice integrating the sine of x to some power times cosine of x to some power dx, where m and n are going to be non-negative integers in this case. So we can divide this up into three separate cases. If m is odd, the power on the sine function is odd, then we're going to use the identity that sine squared of x is equal to 1 minus cosine squared of x to obtain a new format for the integral, and that is that we're going to have sine squared we're going to have sine of mx equal to sine of 2k plus 1x, and that's going to be equal to sine squared of x raised to the k power times sine of x. And we can always rewrite sine squared as 1 minus cosine squared x. And this usually helps us take out that single sign in the integrand and set that up as the opposite of the derivative of the cosine. So when you have m as being an odd power or an odd number, the sign has an odd power, you're going to kind of factor out one of those sine functions, and you're going to use that to set up a u substitution situation. If m is even and n is odd, in other words, the power on the sine function is an even number, the power on the sine or the cosine function is an odd function or an odd number, then we're essentially going to do something very, very similar. We'll go ahead and rewrite the cosine to the nth power equal to cosine of 2k plus 1 power of x, and this is going to be equal to cosine squared to the k power times cosine x. And again, we can always rewrite cosine squared of x as 1 minus sine squared of x. And then we'll combine this single cosine with dx and set up the cosine x dx as equal to the derivative of sine of x, and again, do a u substitution of sorts in order to make the integration easier. Now, if both m and n are even, then we're going to use the, essentially, we're going to use a version of the half angle formulas where we're going to substitute sine squared x is equal to 1 minus cosine 2x over 2, or cosine squared x is equal to 1 plus cosine 2x over 2, and this will reduce the integrand to 1 in lower powers of cosine of 2x. So these are the basic techniques, and we're going to see each of these in action with some examples. So let's see if we can do that. So we'll stop the share and we'll bring up the whiteboard. Okay. So first thing we're going to do is we're going to take the shoot. Let's make sure that we get, there we go. I want this a little bit thicker, maybe. No, okay. We'll leave it curved, and we're going to do a little bit thicker width. This way we can read it a little bit easier. All right, so let me see if I can just kind of move this up a little bit. Okay, here we go. So we're going to take the integral, that's a little bit better, of sine cubed of x times cosine squared x dx. Okay, so what we're going to do is we're going to rewrite sine cubed as sine squared x times sine of x times cosine squared x. dx. And we're going to absorb these pieces into the derivative of cosine x. And because the derivative of cosine yields a negative, we're going to go ahead and stick that negative out here. Now sine squared, again, because I have cosine in my derivative operator, I'm going to change the sine squared to 1 minus cosine squared x. And then I'm going to do another cosine squared x, derivative cosine x. And as you can see here, I'm getting ready to set up this u substitution. So I'm going to go ahead and set up u to be equal to, let me change the color on this a little bit. Set up u to be equal to cosine x. I already have derivative cosine x, so I don't have to worry about doing another calculation because I've already set it up this way. So this is going to give me opposite integral 1 minus u squared times u squared times du, because I've already set it up. See, I already have cosine x for u, so I just plug it in. Now I'm ready to go ahead and do a little arithmetic. We have u squared minus u to the 4th du, opposite integral u squared du, plus integral u to the 4th du. Integral of u squared is 1/3 u cubed plus c1. Integral of u to the 4th by power rule is 1 to the 5th plus c2. Let me go ahead and rewrite that up here. Now these constants of integration, we're just going to combine these into 1, and we're also going to take care of this substitution. We start in x, we end in x. Oops. Got a little ahead of myself there. Where's my eraser? There it is. And this is our result. So when you do a trigonometric substitution that satisfies the first case, we're setting it up for a u substitution by peeling off one of those sine functions so that it can be a derivative of a cosine function. Okay, just don't forget to incorporate that negative. If you do peel off that sine, if you peel off that sine to become the derivative of the cosine, don't forget that negative to join with it. Okay. All right. So this is how one example is done. This is a case 1 situation. Okay. Case 1 situation where sine has an odd power. And see, we separated it in order to make that method visible. So clear. Now, our second one is going to be case 2. Now, remember, case 2 is when you have the integral sine mx cosine n x dx. M is odd and m is even. M is even and n is odd. So for this example, we're going to consider the integral of just cosine to the fifth. Okay, so in this case, m is 0, n is 5. Good to go. So what our rule says is that we're going to take the integral of cosine to the fourth power times cosine to the first power. And again, we're kind of incorporating this part right here to become some derivative of the sine function. So we're setting it up for a u substitution when we do this. Okay? So I'm going to make that u subs cosine x. I've already set it up so that I get this thing here. So we have cosine to the fourth times cosine x dx. We're going to set this up as the quantity 1 minus sine squared x squared times the derivative of sine x. So we're going to let u be sine x now. And we're going to take 1 minus u squared squared du. And 1 minus u squared squared is the same thing as 1 minus 2 u squared plus u to the fourth du. And then we integrate each term, factoring out the constants, if you will. Perform the integration. Plus C1 plus C2, 1/5 u to the fifth plus C3. And again, we have these arbitrary constants that we're going to combine. So we have u minus 2/3 u cubed plus 1/5 u to the fifth plus an arbitrary constant. Now remember, we start in x, so we end in x. So we go ahead and we undo our substitution now. U was sine of x. And there's my result. So again, a very similar case with the this time the cosine having the odd power, the sine having the even power. We do the similar trick of peeling off one of the cosine functions and getting it set up for a u substitution. So once we peel it off, we're going to set up u to be the sine of x, and we'll go ahead and do the Pythagorean identity to change cosine squared into sine squared, or 1 minus sine squared, sorry. And this enables us to do a u substitution, trying to integrate powers on trigonometric functions to integrating something that appears like a polynomial, which is very simple because we just reapply the power rule. And then once we do the integration, combine the constants of integration, then we undo the substitution to get us back to our original variable x. Okay, so case 3 is when both m and n are even. Okay. So if this is the case, let's go ahead and do an example to set us up here. Let's say we take the integral of sine squared x times cosine to the 4th x dx. So if they're both even, our rule says that if I want to take sine of mx cosine nx dx, I'm actually going to make a substitution where where m is even, is going to be equal to some 1 minus cosine 2x. This is one of the half angle identity formulas. Okay, so we've replaced that with 2. So this is sine squared. So this would be some m over 2 power times 1 plus cosine 2x over 2 raised to the n over 2 power dx. And now we're going to integrate these. Don't forget that m and n are even, so 2 will divide into it evenly. So we don't have radicals here. We still have nice even powers. So this is what we're shooting for. So we're going to go ahead and take sine squared x, and we're going to rewrite it as 1 minus cosine of 2x over 2. We're going to take cosine squared x, and we're going to rewrite it as 1 plus cosine 2x, all that over 2. And because this is squared, to get to the 4th power, that means this whole thing is going to be squared. So what we're going to do now is integrate, do some algebra. So we're going to have 1 minus cosine 2x, all of that over 2, times 1 plus cosine 2x, all that over 2 squared dx. So this is going to be equal to 2 times 2 squared, which is 1/8, times the integral 1 minus cosine 2x times 1 plus cosine 2x times 1 plus cosine 2x dx. And when you do all of this multiplication out, this is the difference of squares here. So you end up with 1 minus cosine 2x squared, or cosine squared 2x, whichever you pleasure, 1 plus cosine 2x. Then you have a little bit more, 1/8 integral 1 times 1 is 1 plus cosine 2x minus cosine squared 2x minus cosine cubed 2x dx. And now we can go ahead and integrate this. So we're going to go ahead and separate this out now. So we're going to write this as 1/8 times the integral of 1 dx plus the integral of cosine 2x dx minus the integral cosine squared 2x dx minus the integral cosine cubed 2x dx. So we have each of these integrals to evaluate. Now we're going to need a new slide for this. So these are the integrals that we're going to evaluate. We're going to do them one at a time. So let's go ahead and do a new slide. And we will start off with the easy ones first. So we have the integral of 1 dx, which is just x. Then we have the integral of cosine 2x dx. And again, if I let u be equal to 2x, then du is just 2 dx. So du over 2 is dx. So then we have the integral of cosine u times du over 2, which equals 1/2 integral cosine u du. And the integral of cosine is negative sine u plus some constant. I'll call it C2. So it's plus some constant C1. So this is equal to negative 1/2 sine 2x plus some constant of integration C2. Derivative, antiderivative of cosine is sine. So that's a plus. Let me make a, there we go, that's a plus. Derivative of cosine is negative sine, sorry. So we go this way. And then our third integral. So this was our first integral. This was our second integral. Our third integral is the integral of negative cosine squared 2x dx. So we're going to move that negative out. And then we're going to do our substitution here, where we're going to take the cosine squared of 2x, and we're going to repeat that substitution. 1 plus cosine of 2 times 2x, all that over 2, which is equal to 1 plus cosine 4x, all that over 2. So this is negative integral 1/2 times 1 plus cosine 4x dx. And this is equal to negative 1/2 integral 1 plus cosine 4x dx. Negative 1/2 integral 1 dx. We'll go ahead and put all this in one big bracket, plus the integral cosine 4x dx. And integral of 1 again is just x. 1/2 x plus, we'll just say C3, plus cosine 4x becomes sine of 4x, all that over 4, plus another constant of integration. So our final result for this third integral will be negative 1/2 times the quantity x plus 1/4 sine 4x, go ahead and close that off, plus some arbitrary constant, which we'll just call C5. And that's what the third integral is. So our first integral evaluates here, our second integral evaluates here, our third integral evaluates there. And then we have our fourth integral. Okay, and we'll need a new sheet of paper for this. So our fourth integral was the integral of negative cosine cubed 2x dx. And now we're back to essentially case 2. So this is a case 2 type of integral, and we end up with negative integral cosine cubed 2x dx, negative integral cosine squared 2x cosine 2x dx, negative 1 minus sine squared 2x times the derivative of sine of 2x and we have that times 1/2. Because when I take the derivative of sine, I get cosine 2x times 2, and so the 2 and the 1/2 cancel. Now I'm ready to make my u subs. U will be equal to the sine of 2x, and this results in negative 1/2 integral 1 minus u squared du, negative 1/2 integral 1 du minus integral u squared du, negative 1/2 integral of 1 du is just u plus some constants, we'll call it C6, minus minus 1/3 u cubed plus some constant, we'll call it C7, 1/2 u plus 1/6 u cubed plus some arbitrary constant C8. Start in x and end in x, so u, remember our u substitution was sine of 2x, so we have negative 1/2 sine 2x plus 1/6 sine 2x cubed. Now that's from the third part, plus the arbitrary constant. So combining everything, we get we get 1/8 times the quantity x plus 1/2 sine 2x, and then we get minus 1/2 x minus 1/8 sine 4x. And then we get minus 1/2 sine 2x plus 1/6 sine cubed 2x plus our arbitrary constant. So x minus 1/2 x is 1/2 x. So that takes care of those guys. We have sine of 2x, we have plus sine of 2x minus sine of 2x, minus 1/2 sine 2x plus 1/2 sine 2x. So those are gone, those add to 0. And then we have minus 1/8 sine 4x. And then we have plus 1/6 sine cubed 2x plus our arbitrary constant. Now, if I take a 2 out of each one of these, basically take out a 1/2, just to simplify things down a little bit, I get 1/2 x minus 1/4 sine 4x plus 1/3 sine cubed 2x, and then plus the arbitrary constant. And this is my final result for this example. So as you can see, these integrals can be very long and very tedious. But if you go through it slowly and piece by piece and exercise those formulas, they can be done with minimal stress. You just have to be patient and you have to take your time. Okay, make sure that you go through each term correctly, looking for those substitutions. Okay. So that was our third and last case demonstration with sines and cosines. But what happens if you don't have sines and cosines? What happens if you have something else? Okay, so let's take a look at another example that doesn't satisfy those cases. So let's go ahead and say that we want to evaluate the integral from 0 to pi over 4 of the square root of 1 plus cosine of 4x. Okay. So what we're going to do here is we're going to actually kind of recognize this a little bit as like the top half of that half angle formula. Remember that cosine squared of x can always be rewritten as 1 plus the cosine of 2x, all of that divided by 2. So if I look at this part here and I say, here's a 1 plus cosine of some argument, I have the top half of this fraction. So if I basically let x be equal to, let's just say 2u, then I can go through and say that 2 cosine squared of u is equal to 1 plus cosine of 2 times 2u. This is 1 plus the cosine of 4u, which is exactly what I have here, just with a different label. So this summation can be replaced with that guy right there in terms of x. Okay. So that's what we're going to do. So the integral from 0 to pi over 4 square root 1 plus cosine 4x dx. Using what we've just demonstrated here, all right, we're going to make this substitution. Integral 0 pi over 4 square root of 2 cosine squared 2x dx. Okay. That's the substitution that we made, because 2 cosine squared of stuff is 1 plus cosine of 2 times that stuff. Okay. So we've done our substitution. We've got everything worked out the way that we want it to work out. Now all I have to do is simplify down a little bit. So we have the integral 0 pi over 4 square root of 2 times square root cosine squared 2x dx. Square root of 2 is a constant, so we can factor that out. Square root of something squared is the absolute value. Don't forget absolute value here. And then we double check to see if this absolute value needs to be split into a plus and minus part. Now the good news is that between 0 and pi over 4, okay, so on the interval 0 pi over 4, cosine of 2x is going to be positive. Cosine of 0 is 1. Cosine of pi over 4 times 2 is cosine pi over 2, which would go to 0, but it is positive throughout the entire interval. So we're good on this. Okay, so basically the curve starts at 1 and kind of comes down, but it is positive. Okay, so it's important that you check. Given the fact that it's positive means that I can drop the absolute values. So this becomes the square root of 2, integral 0 pi over 4 of just cosine 2x dx. And now we can go ahead and do the straightforward integration. I'm going to let u be 2x. So du over 2 is dx. And we have square root of 2. When x is 0, u is 0. When x is pi over 4, this is pi over 2. And we have cosine u du over 2. And then we just go ahead and do the integration. Okay, integral of cosine of u is sine of u, evaluated from 0 to pi over 2. Square root 2 over 2, sine pi over 2 minus sine 0 is equal to root 2 over 2. Sine of pi over 2 is 1. Sine of 0 is 0. And you are left with just square root 2 over 2 as your result. Okay. Now, if you wanted to, you could use the formula directly rather than doing another substitution like this and just have this branch off as, you could do this an alternate way by saying the integral of cosine of ax dx is equal to 1 over a sine ax plus c. I mean, you can do it either way, but the derivation of this formula comes from the u substitution. So either way you want to do it. But the result here is root 2 over 2. And again, knowing these trigonometric formulas is very, very crucial to evaluating these trigonometric integrals. So in another video, we will do more examples, except this time we'll consider tangents and secants. So thank you for your time and attention.